In order to calculate forces exerted by moving fluids and to calculate other effects of flow, such as transport, we must be able to describe the dynamics of flow mathematically. To discuss the dynamics, we have to be able to describe the motion itself. The description of motion is called kinematics. We will be interested in the kinematics of continuous media, that is, in describing the motion of deformable stuff that fills a region. Specifically, we'll be interested in describing the displacement, velocity, and acceleration of material points in the two reference frames commonly used in fluid mechanics. We'll show how these two descriptions are related to one another. In addition to moving from place to place, an elementary piece of fluid is generally squeezed or stretched and rotated as it goes. We are going to focus our attention on the translation, not on the deformation. In this flow of water through a contraction, hydrogen bubbles have been used to identify pieces of fluid so that we can follow their motions. These pieces are quite large, however, and we would like to examine the motion of very small, infinitesimal bits of fluid. Therefore, it will be more convenient to have a computer simulate these motions and generate the visual displays for us. We will use open circles, as we are doing here, to identify material points. In elementary mechanics, we are accustomed to describing the position of a material point as a function of time, using a vector drawn from some arbitrary initial location to indicate the displacement. We will use open vectors, as here, to indicate velocity and displacement relating to material points, open points. In a given motion, we can compute the velocity and acceleration of such a point at each instant. Here we indicate the velocity by a vector attached to the point. In a continuous fluid, of course, we have an infinity of mass points, and we have to find some way of tagging them for identification. A convenient way, though not the only one, is to pick some arbitrary reference time, which we will call the initial time, and identify the material point by its location at that time. Mathematically, we would say that the velocity is a function of initial position and time. To accord with this description, we have shown the vector attached to the initial position. We could show the vector attached to the moving point, or use both. If we were displaying the motion of a group of points like this, whose vectors do not interfere with one another. To display the whole motion, and in more complicated situations, we avoid interference by showing the vector only at the initial location. To describe the whole motion, we would have to give the velocity of all the pieces of matter in the flow as a function of time and initial position, like this. This description, in terms of material points, is called a Lagrangian description of the flow. Such coordinates are called Lagrangian, or sometimes material coordinates. From the Lagrangian velocity field, we can easily calculate the Lagrangian displacement and acceleration field. We can imagine attaching an instrument, like a pressure gauge, to a moving point, to make what we might call a Lagrangian measurement. This sort of thing is attempted in the atmosphere with balloons of neutral buoyancy. If the balloon does indeed move faithfully with the air, it gives the Lagrangian displacement. Such Lagrangian measurements are actually very difficult, particularly in the laboratory. We usually prefer to make measurements at points fixed in laboratory coordinates. Classically, the idea of a field, such as an electric, magnetic, or temperature field, is defined by how the response of a test body or probe, like this anemometer, varies with time at each point in some coordinate system. Here we are probing in laboratory coordinates. We will always indicate such probing points, points in a coordinate system fixed in our laboratory, and the velocities measured there by solid points and solid arrows. Here is a grid of points fixed in space. We show the velocity at each point. A description like this, which gives the spatial velocity distribution seen by a probe in laboratory coordinates, is called an Eulerian description of the flow. Although the physical field is the same, the Eulerian and Lagrangian representations are not the same, because the velocity at a point in laboratory coordinates does not always refer to the same piece of matter. Different material points are continually streaming through the same laboratory point. The velocity that a fixed probe would see is the velocity of the material point that is passing through the laboratory point at that instant. It's an advantage of the laboratory coordinates that there's often a frame of reference in which the Eulerian field is steady. Just as we simulated the flow in the contraction, we can simulate the flow under a free surface gravity wave like this. To make things clearer, we have rather exaggerated the wave amplitude. Let's take a closer look. These are moving material points and their path lines. Here are the velocities of the moving points, the Lagrangian velocities attached to the points, and here also attached to their initial locations. In any flow, the Lagrangian field can only be steady if each material point always experiences the same velocity. This degenerate case only happens in a steady parallel flow. Here now is the Eulerian description. In this wave motion, neither the Eulerian nor the Lagrangian description is steady. In fact, they have an identical appearance. In this flow, if we move our frame with the wave speed, the Eulerian pattern will become stationary. Let's do this and indicate the translation velocity by an arrow at the bottom. Now let's resolve the velocities into components. The horizontal component is the velocity with which our frame is translating. The other component is the material point velocity in the original frame of reference. Let's see that catch up again. The path lines, which are also streamlines in this frame of reference since the flow is steady, resemble the form of the free surface. As a material point passes through each laboratory point, its velocity is instantaneously the same as that of the laboratory point. It is partly this possibility of eliminating one of the variables in the analysis, time, that makes the Eulerian representation more attractive. Most laws of nature are more simply stated in terms of properties associated with material elements, Lagrangian quantities. But it's nearly always much easier mathematically, when describing a continuum, to deal with these laws in laboratory coordinates. Thus, to write our conservation equations, we have to talk about transforming from one set of coordinates to the other. Let's talk first about the relation between time derivatives in a scalar field. Let us imagine a river in which a radioactive tracer has been distributed. Since we're interested in local changes, let us look at an infinitesimal part of this river. Now let us imagine that the tracer is suddenly and uniformly distributed in the river. These dots that are gradually disappearing symbolize the tracer, which is gradually decaying everywhere. These filled-in circles represent two laboratory points, which are infinitesimally close together on the same streamline, but which look far apart in our expanded view of the river. Since in this case we distributed the tracer uniformly, the radioactivity at the two laboratory points is the same, but is changing with time. We can add radiation counters at the laboratory points. The solid bars on these Eulerian radiation counters indicate the level of radioactivity at these two laboratory points. We can monitor the level experienced by a material point traveling from one laboratory point to the other by watching the open bar on the Lagrangian counter carried by it. The dashed bar represents the value recorded by the Lagrangian counter as the material point passed through the left-hand laboratory point. Comparing the before and after values of the Lagrangian counter, it is evident that the traveling point sees only the same change that each of the laboratory points sees. This can be written as the time difference multiplied by the rate of change with time. Suppose now, however, that the tracer is not uniformly distributed in the river, but that the intensity is greater upstream. Now the intensity at the downstream point is initially lower, and of course both are decreasing with time as before. Just as before, the only change experienced by the material point is due to decay. The change seen at a laboratory point is not, however, since new material of originally higher intensity is being swept past. To express the change experienced by a material point in Eulerian variables, we need two terms: the change of intensity with time at a fixed point and the intensity difference between laboratory points at a fixed time. The total change when the material point has reached the right-hand laboratory point is given by the difference in level between the dashed counter on the left and the Lagrangian counter. The change with time experienced by either laboratory point is given by the difference in level between the dashed counter and the Eulerian counter on the left, and can be written, as before, as the time difference multiplied by the rate of change with time. The change due to the intensity difference between the laboratory points at any time is indicated by the difference in level between the two Eulerian counters, and can be written as the distance traveled multiplied by the spatial gradient in the direction traveled. The distance traveled can be written as the time difference multiplied by the magnitude of the velocity. The total change is the sum of the two changes described. The material or substantial derivative is the name given to the expression multiplying the time difference. This is simply the rate of change with respect to time seen by the material point as it passes the laboratory point, expressed in laboratory coordinates. Since it is to emphasize that the material derivative is the rate of change seen by a material point as it passes a laboratory point, but expressed in laboratory coordinates. In vector notation, the velocity times the gradient in its direction can be written as the scalar product of velocity and the gradient. We're also interested in the material derivative of a vector field such as the velocity. We're especially interested in that because the material derivative of the velocity gives an expression for the acceleration in a form which we need for the momentum equation. The expression that we just obtained for the material derivative of a scalar field would work just as well for each component of a vector field, but we can also show the material derivative of the vector field directly. Here are two laboratory points infinitesimally close to one another in a magnified view of an arbitrary steady flow. They lie on the same path line, and a material point is traveling from one to the other. The velocity of the material point is indicated by an open arrow attached to it. Clearly, although the flow is steady in the laboratory frame, the moving material point experiences change as it travels to regions where the steady velocity is different. The total change will be the difference between the velocities at the two laboratory points, indicated by the solid Eulerian vectors. The amount of the change will be easier to see if we attach the Lagrangian vector to the left-hand laboratory point, taking as our initial or tagging time the time when the material point passes that laboratory point. The difference between the Eulerian vector and the Lagrangian vector at the left-hand point gives at each instant the change that the material point has experienced. The total change when it arrives at the right-hand point, a vector distance delta r away after a time delta t, can be written as the vector distance traveled times the gradient of the velocity. The distance traveled is just the time difference times the velocity. Now, if the velocity of the entire flow changes with time, as it does here, the Eulerian vectors also change with time. The amount of change will be easier to see if, in addition to placing the Lagrangian vector at the left-hand point, we include as a dashed vector the initial value of the left-hand Eulerian vector. Now, when the material point has arrived at the right-hand laboratory point, the total change it has experienced is given by the difference between the dashed vector and the Lagrangian vector. But this can be broken into two parts. The difference between the velocities at the left and right-hand laboratory points at this instant is given by the difference between the Eulerian and Lagrangian vectors on the left. The change each laboratory point has undergone during this time is given by the difference between the dashed and Eulerian vector on the left. The spatial velocity difference can be written as before as the time difference times the velocity times the gradient of the velocity. The temporal velocity difference can be written as the time difference times the rate of change with time at a laboratory point. To find the total change, we must vectorially add the two effects. The material or substantial derivative is just the expression multiplying the time difference. This is the rate of change seen by the material point as it passes a laboratory point, written in laboratory coordinates. In this way, the acceleration, more simply written in a Lagrangian description, has been expressed in Eulerian notation. To summarize what we have seen, we can tag the material points in a flow by using their locations at some reference time, and then give their displacement, velocity, and acceleration as functions of time and initial position. This is called a Lagrangian description. Alternatively, we can define a coordinate system arbitrarily and probe to find the displacement, velocity, and acceleration at points fixed in that system. This is called an Eulerian description. This has the advantage that it is sometimes possible to find a system in which the flow is steady. It is also mathematically enormously more convenient. We nearly always write the conservation equations for a continuum in this Eulerian system. It has the disadvantage that we're not always referring to the same material point.
We can, however, transform from one system to the other by using the fact that displacement and velocity at a laboratory point is the displacement and velocity of the material point that happens to be there. To express in Eulerian field variables the change experienced by a material point, we must take account not only of the change with time of properties at a fixed point, but also of the change of properties with position at a fixed time.